Hello, so good morning. Our topic today, we will resume our lesson on the nature of counting. And if you remember last time, we discussed permutation. Let's now talk about combinations. And if you remember, the difference between permutation and combination is that for combination, the order does not matter. In order to fully understand combinations, let's discuss the committee problem. So, what is the committee problem? Let us consider the following example of a set of names or five people: Alfie, Bogie, Calvin, Doug, and Ernie. So, in how many ways can they elect a committee of two persons? We we call this the committee problem. We call this the committee problem. So, one method of solution is easy but tedious, and it involves the enumeration of all possibilities. So, if you look closely, we have 10 possibilities, right? 10 combinations. And if you recall last time, for permutations, we used parentheses, right? But this time, we use um, braces to indicate that the order doesn't matter. And if you notice that there's no there um we for example we included AB, but we no longer included BA because we assume now that AB is just equal to BA because the order does not matter. So if you are to be a member of a committee of two people, then the order really of who goes first in the list does not matter because both of you are simply members of the committee. Do you see why we cannot use the fundamental counting principle? Remember the three? We cannot use this anymore. Um, for the election problem that we did last meeting, we found that the fundamental counting principle works. But for the committee problem, we need another formula. Now, for permutation, choosing a president, secretary, and treasurer, the order matters. So Alfie Bogey Calvin is different from Bogey Alfie Calvin because um, they have different roles. But for a committee, all three are members, right, of the same committee. So ABC and BAC are the same essentially. The order is it doesn't matter. So again, no, for a committee problem, for a combination, the order is not important. So when the order is in which the objects are listed is not important, we call this list a combination, and it's represented as a subset of A. So we are actually looking for subsets of A. Example, select two elements from the set A equals A, B, C, D, E, and list all possible arrangements as well as all possible subsets. Okay, so if we list all possible arrangements in permutation, we can see here that we use parentheses in the left side, and there are 20 permutations. But for combinations where the order is not important, we only have half of that, which is 10 possible combinations. And all of these, as mentioned, are subsets of A, B, C, D, E. A, B, A, C, A, D, A, E. They are all subsets or they are sets within the main set. Of course, there are other subsets. When you take three from from the five, then that also is a subset. But here we're just focusing on the subsets with two members. So we now have a definition for a combination. A combination of R elements of a finite set S of n elements is a subset of S that contains R distinct elements. So the notations that we use are N, R, and C and R. And we are going to focus more on the notation that looks like a matrix, a parenthesis with n at the top and r at the bottom. It is more common in our later work in mathematics, so we will use that notation. The notation nr is read as n choose r. The formula for the number of permutations leads directly to a formula for the number of combinations since each subset of R elements has R factorial permutations of its members. Anyway, the formula that we have now is this one. N choose R, or the combination for n set choosing R, is equal to n factorial over R factorial times the quantity n minus R factorial. Notice that the difference with this and the permutation formula is the presence of R factorial in the denominator. So that's the difference between the formulas for permutation and combination. For example, if we evaluate 10 choose 3, what we have is this, no? 10 factorial over 3 factorial times 10 minus 3, or 7 factorial. And to evaluate this, we expand the numerator, 10 times 9 times 8 times 7 factorial. And we also expand the denominator, 3 times 2, and keep 7 factorial. So they cancel out. And what we are left with is 10 times 9 times 8 divided by 3 times 2, which is equal to 120. For this example, n choose 0, n factorial over 0 factorial times n minus 0 factorial. What we have is n factorial over 1 times n factorial. So the n factorial in the denominator cancels out with the 1 in the numerator. So what we are left with is 1. So, right. So if you choose 0, that combination is equal. There's only one possible combination if we choose 0 from a set, because what we get is the empty set, right? And the empty set is also a subset, but that's just one subset. So the answer is 1. Here is a more algebraic version. M minus 1 choose 2. Notice that the numerator, m minus 1 factorial, can be expanded to m minus 1, m minus 2, m minus 3 factorial. Because with the factorial, you're subtracting 1 for successive terms. So if you subtract 1 from m minus 1, you get m minus 2. And then if you subtract 1 from m minus 2, you get m minus 3. Anyway, canceling out m minus 3 factorial for both the numerator and the denominator gives us m minus 1 times m minus 2 all over 2. So the Pascal's triangle, if you remember the Pascal's triangle, remember that it is a pattern. I don't know if you remember this, but I don't have a pen. Anyway, annotate. Let's see if I can annotate. Yo, I don't know. So it starts with 1, 1, 1, 1, 2, 1, right? 1, 3, 3, 1. Do you remember the Pascal's triangle? 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Do you know how I did this? What I did is I added the subsequent numbers beforehand. So 1 plus 1 is 2. So that's why there's a 2 there. 1 plus 2 is 3. And 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. You see the pattern? 4 plus 6 is 10. And apparently, the Pascal's triangle is related to... Oh, how do I remove the annotations? How do I now remove the annotations? All right, there it is. It's related to the combinations. The very peak number in the Pascal's triangle is actually a 0, 0 combination. And then the first row, 1, 0, and 1, 1 choose 1. And the second row, 2 choose 0, 2 choose 1, 2 choose 2, and then 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, and then 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So do you see the pattern? So the Pascal's triangle, apparently each item is a combination. So that is n choose r is the number in the nth row and the rth diagonal of the Pascal's triangle. So as you can see here, we now choose the very peak. We now label it as row 0, and then the next level is row 1, 2, 3, 4, and so forth. And the diagonals are labeled 0, 1, 2, 3, 4, 5, 6, 7, and so on. So there are two diagonals, but essentially, um, um, each intersecting row and diagonal is the same, regardless if you use left diagonal or right diagonal. Let's see. For example, 8, 3. 8, 3 means row 8, diagonal 3. And if we look at the Pascal's triangle, row 8, diagonal 3 is 56, regardless of if you use the left diagonal or the right diagonal. You should check that out. Where row 8, diagonal 3 intersects is at 56. And where 6, 5, 6 choose 5 is row 6, diagonal 5. Where that intersects is at a value of 6 in the Pascal's triangle. So let's look at row 6, diagonal 5. You will see that they indeed, whether you choose the left diagonal or the right diagonal, they intersect at um, row 6, at the number 6. Okay. Okay, I'll be